Hello, everyone. Today, I'm going to be talking about the Merchant API, better known as MAPI or MAPI. And my name is Jad Wahab. So I'm going to begin with what exactly is the Merchant API, and then I'm going to talk about why is it important, how it works, and how would someone go about using it. So what is the Merchant API? What is MAPI? So in simple terms, it's basically just an interface into Bitcoin nodes or miners. And most of the time, it's going to be merchants who are interfacing with the Bitcoin nodes, and we'll see why in a few minutes. And through the Merchant API, nodes can easily offer services to merchants with the goal of making Bitcoin transactions peer-to-peer much easier. And because at the end of the day, the title of the Bitcoin white paper is Bitcoin peer-to-peer electronic cash system. So why is it important? To understand why it's important, we need to talk about a bit of background around Bitcoin scaling and peer-to-peer transactions and peer-to-peer network. So a bit about Bitcoin scaling. This right here is an email thread between Satoshi Nakamoto, the inventor of Bitcoin, and Mike Hearn, which was an early Bitcoin developer. And this here was in 2009. And in this email thread, Satoshi goes on saying that the existing Visa credit card network processes about 15 million internet purchases per day worldwide. And Bitcoin can already scale much larger than that with existing hardware for a fraction of a cost. Never really hits a scale ceiling. So at that time, that was 2009. Right now, we're in 2020. And basically, there's been a lot of things that have gone on in the past 10 years, but we're finally back to scaling the way Satoshi envisioned. And on the scaling test now, we've got around 1,300 transactions per second, and it keeps on growing. I think a few weeks ago, we had 369 megabyte block on the mainnet, and it's just going to keep on scaling. And then in this email thread as well, Satoshi goes on to talk about how at that time transactions were free, but he clearly understood the importance of fees and how they would develop on the network. So he goes on talking about that at the moment, the fees, there are no fees for Bitcoin, but afterwards, as Bitcoin running a node becomes more burdensome, miners are going to only accept transactions with fees, which is what we see, which is what is the case today. And the owner of the node would decide the minimum fee they'll accept. And users would get faster acceptance if they include a fee and slower if they don't. And we'll see this more clearly throughout the presentation, but it's just an important thing to remember now. So to continue understanding how Bitcoin scales and how the Merchant API is important, we need to talk about how we got to where we are right now. And so when we started off with Bitcoin, the way a customer would send a transaction to a merchant was completely unscalable. So this is the sort of legacy way. So if a customer wanted to send a transaction here to a merchant, they would have to send it to the Bitcoin network, which is this diagram in the middle. They would send it to the Bitcoin network, and then the merchant would have to listen to all transactions on the network and then scan them to find the transaction that he's looking for, and then drop all of the rest. So obviously, as the Bitcoin network scales, this technique is not going to work out. So it's never going to be scalable if the merchant has to listen to all transactions ever happening in the world to be able to find the transaction that he's interested in. So as we move towards the way Bitcoin was originally envisioned by Satoshi, we come to realize that transactions should be done peer-to-peer. So a customer would send a transaction to a merchant directly, and then the merchant would then send that to the network. So the merchant or the receiver of the money is the person who has to settle the transaction on the blockchain. So it's the same concept as a check. So if you want to send someone a check, you hand them the check and then they have to go and cash that check. So you don't basically send the check to the bank for them if you want to send them a check. And then, so the merchant who needs to settle that check needs to do it in the most efficient way that they need. For example, if they need to get that transaction settled immediately, they would have to get it settled quicker. So they would have to require much higher fees. And if, for example, they were an online retailer that they wouldn't ship the goods, for example, in a few days or weeks, then they don't require that sort of speed to settle the transaction, so they can afford to have a lower fee. So basically, this Merchant API is one of many tools that we'll see that just make peer-to-peer much easier and more secure, along with other tools, for example, Paymail, BIP270, and we'll see a couple and more as we go along in the presentation. So the merchant is the one that has to be in charge of settling that transaction. And in the past, we've seen a lot of sort of controversy around double spending. But before we get into sort of the security of how merchants need to cash their checks or settle their transactions, let me just briefly describe double spending and just the background of how things developed. So in the past, everyone used to basically model the Bitcoin network as sort of a mesh. So these are the nodes on the mesh, and then one of the nodes would send a transaction or a block, and then it would propagate to the rest of the network in a mesh structure, the way you can see in this GIF. So as time progressed and as we studied the network and monitored the network and understood it more clearly and more deeply, we realized that the Bitcoin network is actually a small world network with highly connected graphs, as we can see in this diagram here. And the miners or nodes are highly and densely connected. And the reason behind this is because miners or nodes are highly incentivized to connect to as many other miners as possible. And this is because miners are always racing to find the race and to find and propagate the new blocks, and every single second counts. So every 10 minutes on average, Bitcoin miners basically find a new block to add to the blockchain. And it's not enough to just find that block. You need to make sure as a miner that that block gets to everyone else on the network as soon as possible before a competing block replaces your block and you lose all of the fees, basically. So this GIF shows an example of the way a wallet here sends a transaction to the network. So because Bitcoin miners are so densely connected, in like less than 3 hops, your transaction will get to all of the Bitcoin mining network. So it's really quick and really highly connected, unlike the mesh that we previously thought Bitcoin network was. So this is an example of a double spend transaction. So this more clearly models the legacy way, not really the P2P way, which we'll see more clearly, but this is an example of a simulation of a double spend. So what a double spend is basically, if someone is trying to settle or send a transaction to the network, a double spend is like another transaction which is trying to spend the same funds. And let's just go through this GIF right here. And it's a bit quick, so I'm gonna explain it a couple of times. So the original node here, the original like wallet or whatever, sends a transaction to the Bitcoin miners, and then another, this could be the same person, which more likely is, because they have, the only person who has the private key is the person who owns the funds. So would spend another transaction sending the money to somewhere else, and then immediately the miners will be notified of the different transactions. So we'll see that in the next slide that this is not really that accurate, because this model is the legacy way, not the P2P way. So this is not really clear if it's the customer or the merchant. It should be the merchant who should be settling their transaction. So in the next slide, this is basically the more accurate way of modeling the double spend situation. So this is a rogue customer basically that is trying to send a transaction to a merchant. And then this red transaction is the double spend, so which is a transaction sending the money back to themselves. So imagine a check being sent to, let's say, Amazon, and then before Amazon is able to cash the check, you basically take all your money out of your account, and we know that as a check bouncing, and in many countries that's a criminal offense. So in this case, you can see the customer trying to send a transaction to the merchant, and then as soon as the merchant tries to settle that transaction, it's going to be really clear that there's another competing transaction on the network. So basically, in order for the customer to scam the merchant, they have to get their double spend transaction in such a tiny span before the merchant can send their transaction, and it's almost like impossible to time it because of like network delays. And plus, just taking this situation a bit further and taking a step back and looking at security, it's not always the best idea in security to try and prevent. It's a lot of times just good enough to notify. So if, as shown in the diagram here, as soon as the merchant tried to cash the check, the network has seen another transaction, and then the merchant will be notified that there's a double spend transaction, and then the merchant will basically realize that this customer is trying to defraud them and not sell them any goods, and take basically action. And so if we take a look at how security is, there's no such thing as 100% security. So if you understand security properly, you'll understand that it's always a matter of risk and costs. So like if we take a look at this graphic here, this is what many people sort of envision. A laptop is encrypted, and a hacker would basically build a $1 million cluster to crack it. And because it's like uses like 4096-bit RSA, the evil plan is basically foiled. But what actually happens in real life is basically security. It's always the weakest link, which is the human and the human element of it, and it's all about sort of costs. So this is obviously breaking 4096 bits of RSA encryption is going to be really expensive. So what the hackers usually do is basically you can drug the victim and then hit him with a $5 wrench until he tells them the password. So like security is all about risks and trade-offs. So there's always a trade-off between security and usability. So the more you have security, for example, the more features of security like two-factor authentication or extra layers of encryption and more bits of encryption, the harder it is for usability. So it's harder to get into your account when you have two-factor authentication or the encryption is slower. So there's always like a balance. And then as someone developing solutions, you need to basically weigh off these trade-offs and get the optimal sort of threshold. So you shouldn't basically over-engineer things and try to get them more secure than they have to be, because a lot of times you're going to sacrifice usability. And yeah. So with the Bitcoin network, here we know that there's always only going to be one transaction that's written to the blockchain, because that's how the blockchain works. You can't have double spends written to the blockchain. And as soon as one of the nodes finds a new block, then that block is going to include one or the other. So we basically know that Bitcoin does a great job of settling on which transaction is the one that's going to be settled on the blockchain. So we can take that assumption and work off of that. So we don't need to basically have the nodes settle the transaction for us, which is where a lot of the over engineering has become, and people have been trying to sort of add functionality into the node to try and find out which transaction is a double spend and stuff. And as we'll see in the next slide, that's a bit of over engineering. And it's enough to basically just notify the merchant that there is a double spend. You don't have to basically prevent the double spend from happening. So if we look at this diagram again, as soon as this transaction gets broadcast to the network here, this node will talk to this node, and then this node will reject that transaction, and this node can basically notify this wallet that this transaction is a double spend, or there's another double spend on the network. And this is something where we'll see Mappy help out with that. And then as soon as the merchant knows that there's a fraud attempt, that's more than enough. And it's basically, it's not the job of the node to be the arbiter of truth. So nodes settle transactions, and they do a really good job of that, because they add blocks to the blockchain, and for the rules of blocks to be added to the blockchain, one of the rules is that no double spends can occur. So nodes settle the transactions properly, and it's not their job to be the arbiter of truth and find out which transaction is the truthful one. It's basically the job of the merchant or the receiver of the transaction to settle their funds properly. So an analogy is, for example, you can try and for example, cash a check through the mail, and it's not the bank's fault if your mail gets lost. It's your responsibility. So and here a lot of people basically talk about sort of theoretical attacks on double spending, and as we know, there's never been until now a successful double spend defrauding attack. So we just need to basically look at the difference between theory and practice. A lot of people say theoretically, you could pay a miner to mine your double spend transaction, or like reverse your transaction, but it's just it's not practical at all. I mean, if we look at here, this is a picture of a huge mining farm. So miners invest millions, hundreds of millions of dollars in their business, and they're not going to basically sacrifice their business just to double spend your transaction, sending coffee or whatever back to yourself. And for example, any significant payment is not going to happen instantly anyway. That's the first point. And the second point is any significant transaction involves like identities. So if you're going to, for example, if I sold you my house and then you paid miners to go and then reverse that transaction that was sending me the money, do you just think that you could, for example, get away with it like nothing happened? That's just not practical. And miners are obviously not anonymous entities. So as we said, they're spending millions of dollars. They're not gonna sacrifice their whole business just to, like as mentioned in the Bitcoin white paper, the nodes are properly incentivized. They're not gonna, they basically get paid in Bitcoin. They're not gonna do something that harms the network that they get paid in. It's just illogical. And also there's services like insurance. If you still want even further guarantees, if you're a company, for example, handling many quick payments or something like that, you could get insurance. There's already companies on in the space that do that. For example, Gap 600 and Mappy is a tool that could help increase security in that as well, because it's an interface to miners. And as we will see, miners can, through that interface, offer services like double spend, alerts, and other stuff that can make your settling of transactions much more secure. So you can think of Mappy as sort of like an ATM for banks to cash your check with the miners through this interface, which is like an ATM to banks, ATM to nodes. So I quite like this quote by Dr. George Denezis about the principles of computer security. And he says that a system is secure if an adversary within a specific threat model cannot violate the security policy. So as we saw, all security is a matter of risk and cost. So if you really need instant transactions, already there's high guarantees that your transaction will be settled. But if you want further guarantees, you can basically add extra security through the services that I'm going to discuss in the next slides. And it's all about risk and cost. So if you have just, for example, if you're selling coffee or whatever, then you need to basically think about your risk and your cost. It's going to probably cost an attacker much more money than they're going to get out of basically stealing a coffee. And if you're going to be buying something much more expensive, then it's going to take longer, and then it's basically the risk balance out there. So having the interface to Mappy can help with instant transactions, but not all merchants or people receiving money need instant transactions. Some, for example, online retailers or people writing data to the blockchain, they don't need fully instant transactions, and they can afford to pay lower fees and at the sacrifice of getting their transactions settled immediately. So that's also an avenue where Mappy can help out with by the nodes offering services. So some examples of these services. So the first one was the one that we discussed a lot, which was the double spend protection alert, which is for merchants or people receiving transactions to get instant security of someone trying to defraud them. And another service which is in the pipeline now is Merkle proofs, which are also known as inclusion proofs. So once you settle your transaction on the blockchain, you can, as soon as it's mined into a block, get an inclusion proof, and then you can prove that your transaction was mined at a specific point in time if you have the chain of headers, your SPV chain of headers, as basically described in the Bitcoin white paper. And the Bitcoin chain of headers is really small. It grows at about 4 megabytes per year. So basically, you'll be able to prove that a transaction was mined at any point in time, and it was in the blockchain at any point in time by having the inclusion proof and as well as the chain of headers. So it can be done on any really small device. It's not expensive at all. So this Merkle proofs is in the pipeline. It's on the way. It's a bit more complicated than it seems, because there's a lot of things that need to be done properly. For example, the standards committee is in the process of getting the Merkle proofs standardized so that we can have standardization across the whole industry, because there's many different ways of sort of representing the inclusion proof. So just to have it done in a standard way, and also like a callback mechanism, which is in the pipeline, because you never know when your transaction is going to be mined into a block for sure. You just, it's on average 10 minutes per block, but sometimes blocks take, for example, much longer to be mined. So you need to be notified once a block is mined, and there has to be like a callback sort of mechanism to notify you once a block has been mined. And another service that miners can offer is real-time notifications. So for example, if you're waiting for a type of transaction to be mined onto the blockchain, you can receive notifications. You can, like miners can obviously get very creative, as we'll see in the coming slides, and they can offer different services. So the whole idea is Mappy is just to be an interface into the miners, because as we've seen, you don't need to be a node to interact with the Bitcoin like network. So other services they can offer is, for example, as we've seen in the Genesis upgrade, the end lock time and end sequence fields of a transaction have been restored, and that opens up the door for a lot of more use cases. For example, payment channels, and end lock time is basically a lock on a transaction. So you could send someone a transaction and have them only be able to spend it after a certain period of time. So for example, when developing the Bitcoin node software, an engineer was asking how long should we sort of store the end lock time transaction. If someone sends a transaction with end lock time a year in the future, for example, should all miners store that? The answer is it depends on what services the miners are offering. So some miners can offer a service to store your unlock time transaction for a year or however long they want to, but it's by no means mandatory. They can just drop your transaction because it costs money to store a transaction. That's not giving them anything until it's basically time for it to be mined. So I kind of like how Tal are moving away from the word miner or even node and moving towards transaction processors, because over the years, the words miner and node have been very sort of confusing. A lot of people have used them in different ways, and it's just a lot clearer now. And I really think that miners need to be much more active. I think it's not the way it used to be in the past, where a miner could, or a mining pool or whatever, could just download the Bitcoin software and then plug in like a bunch of ASICs and then take a holiday on the beach. It's the block rewards are decreasing over time, and especially after the halvening a few months ago, a lot of the miners' revenues were reduced. They were actually cut in half. So it's going to be very exciting to see what will happen in the future with miners basically trying to make their business strategies more profitable and more basically efficient. So they're going to have to start thinking more long term, and a better way of having a business strategy is a more secure way, obviously, is to count on transaction fees instead of block rewards, because that's diminishing and you can't just rely on the block reward and the price of Bitcoin to just keep going. It's keep increasing exponentially. It's not a very viable business strategy. So as we'll see, transaction processors or nodes will have to offer more services and employ in-house devs and take things into their own hands and stop being too passive. So another reason why Mappy is really important for the node software, the Bitcoin node software, is because the Bitcoin node software, Bitcoin D, has always been a huge monolithic structure. And basically, Mappy is the first step towards basically compartmentalizing the node, because it takes out the fee module of the node, and then instead of submitting your transaction to the node directly, you would have to go through Mappy, which is the fee module that calculates the fee, and through this extension to the send raw transaction RPC call, where you can send a transaction without checking the fee to a node. It makes this fee module able to be a component outside of the node, basically. And this, it's in a way that the first step towards the Bitcoin node software becoming a microservices architecture, which is on the road to be being changed to called Teranode. And it's a new like system architecture of how the Bitcoin node can run at huge scale in a microservices sort of system. So how does Mappy work? In April, we released a public beta on Bitcoin SV's GitHub. So we released a BRFC, which is basically a Bitcoin request for comments, and a reference implementation in Golang. So you can head over there and take a look at the specification, the BRFC specification, and the reference implementation. We'd love to get some feedback. If you have any feedback, you can create issues on the repo, or you can join the Telegram support group, and we're always on standby there. The Telegram support group is linked on both of the repos, so you could just head on over there. So this is a Swagger UI of the Mappy interface. So it's at the moment very simple. There's only 3 calls. There's a get fee quote. So this is where you basically discover what the merchant is charging fees. So in order to figure out how much you as a merchant or a receiver of a transaction need to include as a fee in the transaction to get settled based on the risks that we discussed earlier, and how quickly you want your transaction to be settled, you need to find out how much the miners are charging fees, and that could change over time. So once you've basically created your transaction, there's a post REST call to submit your transaction, and then afterwards there's a get to query the transaction status to figure out if it's been mined into a block, or like basically what's happened to that transaction. So this is a more in-depth data flow of how the merchant API fits in with the bigger picture of peer-to-peer transactions with BIP270 and Paymail. BIP270 and Paymail work hand in hand, and it's basically a mechanism for peers to discover each other and send transactions peer-to-peer to each other. So just a quick look over this. So this diagram is also in the spec, so you can take a look at that afterwards as well. The main idea is the customer and the merchant. So the customer wants to send money to the merchant. They would click pay now basically on the website or wherever, and then the merchant would request a payment, have to request a payment from the customer, and if they're using Paymail, they would request a payment from the Paymail. This right here is Paymail service discovery, and then once they found out where they have to pay the customer to and what script they need to pay, they would get the fees needed from the Mappy, so here, and then request a payment from the customer's wallet, and then once they authorize that, they would send the payment back to the merchant peer-to-peer, and then the merchant would post and submit the transaction to the miner directly to settle it. And then afterwards, they can query the transaction status. So these are the 3 calls discussed in the previous slide. And this is basically how the peer-to-peer transaction sending on the Bitcoin network should look like. And so in the MAPI calls, miners can also sign their responses to make it even more secure. So to understand how miners would sign their transactions, we need to understand miner ID. So miner, because they would sign transactions with their miner ID. So miner ID is basically, it's just a way for miners to cryptographically identify themselves through the Coinbase transaction. So in the past, miners could just basically put any data in the input of the Coinbase transaction, which is the transaction that pays them money for mining a block. So because the input is spending nothing, because they're creating money to send themselves, they could put anything in there. And in the past, miners have basically, that's how they've identified themselves. But there is no security in the way they identify themselves. Anyone could impersonate anyone. You could put anything in there as a miner, as we've seen. This is, for example, Spider Pool. So the idea of miner ID is to basically put some cryptographically identifying data in the Coinbase, which is basically a signature and a public key. So your miner ID is just, in simple terms, your public key and a signature on specific data. So here, this is the miner ID of Tal. This is their public key, and then they could have whatever data they want in there. And there's a bunch of extensions for miner ID that you can check the specification of as well. And in the miner ID, they could also have the MAPI endpoint here. And this fits in with like client wallets. Well, we won't have time to get into that today. But so the idea is, once miners put their public key into the block, identifying themselves, they can use the private key associated with that public key to sign data as themselves. And the idea is they can sign the MAPI responses with this private key. So since we're using JSON for the MAPI system, it's a bit tough to sign data, because as we know, as we'll see in the next slide, JSON is a bit problematic. So we developed something called JSON Envelopes, and there's a BRFC on the Bitcoin SV GitHub repo if you want to see more details, but I'll explain briefly how it works in the next slide. So as we know, JSON is not deterministic. So if you have a JSON with 2 fields, name and color, you could basically flip the name and the color. You could add spaces in there, carriage returns or whatever. So like here, so all 3 of these JSONs are JSON objects are equivalent, but in order to sign something cryptographically with ECDSA, it has to be deterministic, because if you change 1 bit in what you're trying to sign, the whole signature is going to change and you won't be able to verify it. So you need a way of making the JSON object deterministic in order to properly sign it. So we came up with JSON envelopes, which is basically a way of putting the JSON object in another JSON object, which is where the name envelopes comes from. So you would stringify the JSON object and then put it as a payload of another JSON object with the signature as another field on this piece of data and the public key. And then you could choose different encodings, but this is how we get around that situation. And onto the fee spec BRFC. So in the past, Bitcoin didn't really have many fee specs, different fees. So everyone would charge a specific 1 Satoshi per byte. But as we go to less than 1 Satoshi per byte, we get into like decimals, and that thing makes things a bit harder. So we developed a deterministic transaction fee calculation where we use integer maths, because as we know, floating point numbers are not the best for accuracy. So you can check the specification, but what we do is we, instead of saying, let's say 0.5 Satoshis per byte, we would say 5 Satoshis per 10 bytes. And then these are the steps to determine the fee. We use integer maths, and then we floor the answer so that the customer never underpays by 1 Satoshi, and that's never an issue. And just for proper convention, we recommend that the bytes be a power of 10, just to make things more standardized and clearer. So this is where you would calculate a fee as a merchant, or someone is creating the transaction to the merchant. But different, like miners can offer different services for different fee types. So for example, at the moment we have standard fees and data fees, because as we know, you can encode data in Bitcoin transactions in op return outputs. So that data can be pruned by miners. And it doesn't have to be validated by miners in the Bitcoin script. So they can choose to offer lower fees for that. And at the moment, some miners are doing that. So you can have, for example, a standard fee of 0.5, and then another fee which is much less for data fee. So this is how the transaction looks. You have inputs here and outputs, and everything that's not a data output, which is the data that's in the op return, would be priced in standard fees, and this would be priced in data fees. So for more details, you can go to the BRFC spec on GitHub and see an example of how this would work under the hood. So you might be wondering, how could you use MAPI? So at the moment, there are a few services that are connecting to MAPI, and there are a few miners who are actually implementing MAPI along with their nodes. So the first is TAL, which is sort of leading the way with this MAPI and Bitcoin services, and they were the first miner to implement MAPI, and they've also added a few extra services, so user-based fee policies, and they've been creating deals with specific miners to give them lower fees for specific transactions or a specific number of transactions. So for example, if you have more transactions, you could get a discount on some of the transactions, or it all depends on the agreement with the miner. And then we also have Mempool and Dot Wallet, who are also leading the way with implementing Merchant API. And third of all, so far, we've got Matterpool, who recently mined their first block. So congratulations on that. And they are also have their documentation here at Matterpool. And we've got other services like What's on Chain and Unwriter's Minercraft, which are basically connecting to a bunch of different miners merchant API to get, like, for example, if you want to see a bunch of miners, how much they're all charging, or if you want to see the highest fee or the lowest fee, you can go through What's on Chain or Unwriter's Minercraft. So thank you for your time, and yeah, I don't know if we have time for Q&A, but if we do, yeah.
We've got time for a couple of very quick questions. If you just want to unshare your screen so I can show the questions.
Okay.
Okay. So, oh, I've just made the question disappear instead of highlighting it. Okay. So yeah, we are a little short on time, so I'm just going to give you one quick question, and there's one here that I might answer myself, actually. As somebody who seems to be quite familiar with a lot of APIs, how does the merchant API compare with the Insight API?
So I think the Insight API is sort of like the Matter Cloud API, which is like the Matter Pool API, and it's just sort of like the What's on Chain API. It's not really an interface into the miner directly. It's sort of a second layer. So you would go through the Insight API or What's on Chain or Matter Cloud, and then that's a second layer into the merchant API. But MAPI is a direct connection to the node or the miner. So that's how it would compare.
Okay, that's a good explanation, I think. So Adam asks, in underdeveloped countries where internet access is limited, too slow, high latency, could be interrupted, etc., what are the scenarios of double spending and the solutions? I've got some thoughts on this, but Brad, Jad, do you want to have a crack at this one first?
Sure. So it all depends on the cost and the risks for the merchant. So if the merchant has limited, too slow, or high latency, then, for example, they are going to have different solutions than other people. So they can, for example, use different techniques to solve that situation, and they can also pay for insurance, for example, which I covered before, but it depends on what they're selling. So if they want instant transactions, then they can offload a lot of that to, for example, a service like a secondary service that can be online always and monitor like transactions. So and also with the SPV, offline SPV, which is something that we have presented in a previous conference, and we have a patent application on that as well. It's a technique for basically settling SPV transactions when you're offline. So I don't know, you want to add something to that, Steve?
Well, I just add that the SPV inclusion proof is really important here, because if wallets are routinely exchanging those proofs when they send transactions to each other, what that proof actually is a digital signature, effectively a signed confession if they attempt some fraud on you. And the Merkle proof is what links it back to some identity and some history in the blockchain. So for small amounts, offline transactions, there's the incentives don't really line up for anybody to try, simply because there is a mechanism, a recourse mechanism, I suppose, for the merchant, which is true of any payment system today. If you walk into a shop and use a stolen credit card, for example, mechanisms exist to disincentivize that kind of behavior, and I think Bitcoin can do it better.
Yeah, exactly. Just to add a quick thing there as well, if you have the Merkle proofs of the inputs, then you can verify that a transaction is valid, and then all you know is you have enough information to know that the transaction is valid, and then you just don't know that there is another double spend of that. But also, for example, you go on airplanes, and then you can buy things with a credit card on airplanes, which is sort of the same thing as this, and it costs more, and it still works.
Exactly. Now, so consider the scenario where you're in a place that has very poor connectivity. Either the person sending you the transaction also has poor connectivity, or if they don't, they also, if they happen to be connected but you're not, there's always the option of them submitting the transaction to a miner and returning a valid miner ID signature to you, which they can't forge. So as long as you actually know the current miners, which is somewhat equivalent to knowing you know, recent block headers, you've got a level of assurance there that transaction has actually already been sent to a party that you're reasonably assured is honest, and not simply having to rely on the individual that you're transacting with. So I think we need to wrap that up there, because we have our next speaker almost ready to go. It's nChain's Director of Research, which with some notes on network theory. So thank you very much, Jack.
Thank you.